In 1986, a builder in southern France cast a wall from chopped plant stems, powdered lime, and water. That wall is still standing. It is still regulating the humidity inside the building without a single mechanical system. And it is still carbon negative, meaning it has stored more CO2 than it ever cost to produce. That is not a prototype. That is a building with 38 years of performance data behind it, while the fiberglass inside most American walls quietly loses R value every time someone takes a shower. Here is what you will have by the end of this. A clear picture of what hempcrete does that fiberglass physically cannot, exactly why American building codes still make it nearly impossible to use, and the one legal shortcut that changes the math for anyone who wants to build with it today. Quick challenge before we go further. Hold a number in your head. What percentage of conditioned air inside a standard American home escapes through the building envelope every single hour? We will come back to that. And when we do, it is going to reframe everything you think you know about wall performance. Picture a factory floor in 1938. The goal is not to build the best wall. The goal is to build a wall fast enough and cheap enough that an entire nation of returning soldiers can be housed inside a decade. Owens Corning had just begun mass-producing fiberglass insulation, a product invented almost by accident when a researcher named Dale Kleist accidentally directed a high-pressure steam jet at a stream of molten glass and produced a spray of fine fibers. The material trapped air. Trapped air resists heat transfer. That was enough. What the system was never asked to do was regulate moisture, store heat, or last without degrading. It was asked to be cheap, light, and fast to install. On those three criteria, it delivered. The American residential construction industry built itself around fiberglass, and the incentive to find something better evaporated once the economics locked in. The answer to that challenge: between 25 and 40% of conditioned air escapes through the average American building envelope every single hour, according to the U.S. Department of Energy's Building Technologies Office. The material filling most of those walls has not been substantively redesigned since Kleist's accident in 1932. Speed built American housing. Speed also broke the wall. Hempcrete is not insulation in the sense that fiberglass is insulation. That distinction matters more than almost anything else in this video. The material is a composite. The woody inner core of the hemp plant, called the hurd, or shiv, mixed with a lime-based binder and water at a ratio of roughly 4 parts hurd to 1 part binder by volume. Those three ingredients produce a lightweight, mineral organic matrix that sets over several weeks through a carbonation process in which the lime reabsorbs CO2 from the air and slowly returns to its original limestone chemistry. The per-inch R value of hempcrete sits at approximately R2.5, broadly comparable to fiberglass. Anyone who stops the comparison there is missing the entire point. Fiberglass is a pure resistor. It slows heat moving through the wall. Hempcrete is a thermal mass material. It absorbs heat during the day and releases it slowly at night, flattening the temperature curve inside the building across the full 24-hour cycle. That is not a subtle performance difference. That is a different category of wall behavior entirely. Fiberglass resists heat. Hempcrete manages it. A 2019 study published in Construction and Building Materials tested hempcrete walls against lightweight timber frame walls under identical external conditions. The hempcrete walls reduced peak indoor temperatures by up to 8 degrees Celsius. Not 8%, 8 degrees Celsius. Every degree shaved off that peak is a direct reduction in the mechanical work your cooling system has to perform. An 8 degrees Celsius reduction in peak indoor temperature can translate to a 20 to 30% reduction in peak cooling demand, according to thermal modeling published alongside the 2019 study's findings. That is not insulation performance. That is climate regulation built into the wall itself. The moisture performance is equally distinct. Hemp hurd is hygroscopic. It absorbs atmospheric moisture when humidity rises and releases it when humidity drops, acting as a passive buffer built into the wall structure. Research published by the University of Bath's BRE Center for Innovative Construction Materials consistently found lower mold spore counts and lower volatile organic compound concentrations in hempcrete buildings than in equivalent timber frame structures. The lime binder reinforces this lime is naturally antifungal, giving mold no surface to colonize. The wall does not just slow heat, it reschedules it. If your cooling costs spike every July, the fill inside the frame is probably the diagnosis, not the thermostat. In 2004, a family in the Lot-et-Garonne region of southwest France completed a hempcrete renovation of a stone farmhouse that had been in the family since the 1800s. The interior walls had shown recurring damp patches and surface mold for 2 decades. A local builder removed the modern vapor-resistant render, cast hempcrete against the interior face, and finished with a lime plaster. The damp patches did not return. The mold did not return. A follow-up building survey in 2018 documented no condensation-driven deterioration and measured indoor relative humidity consistently between 45 and 60%. The range, the World Health Organization, identifies as optimal for respiratory health with no mechanical humidity control in operation. And then there is the carbon story. Concrete production generates approximately 8% of global CO2 emissions annually, according to the Global Cement and Concrete Association's 2022 report. Spray foam uses blowing agents with global warming potentials between 300 and 1,000 times higher than CO2 per EPA classification data. 1 ton of hemp fiber, by contrast, sequesters approximately 1.62 tons of CO2 during its 1-2 week growing cycle, according to life cycle analysis published in the Journal of Cleaner Production in 2017. A 2,000-square-foot hempcrete home sequesters an estimated 20,000 pounds of CO2 in its walls, roughly equivalent to taking 2 average American cars off the road for a full year. 12 weeks to grow, a century to store. We are halfway through, and what is coming next is the part most channels skip: the actual reason hempcrete is still nearly impossible to build with in the United States, and the exact moves that can get you around it. If this kind of material history matters to you, the stuff that outperforms, costs less, and got sidelined anyway, subscribing now means the algorithm keeps sending it your way. Hit the button and stay in. The regulatory story is where this gets genuinely strange. Why would a government ban a plant that produces a superior building material, a textile fiber stronger than cotton, and a documented food crop, and keep that ban in place for 81 years, while allied nations built entire construction sectors around it? The Marijuana Tax Act of 1937 was passed during aggressive lobbying by petrochemical interests, most prominently DuPont, which had recently patented nylon, and by Hearst newspaper and timber interests, which stood to lose paper market share to hemp-derived pulp. Congressional testimony conflated industrial hemp and its psychoactive relative deliberately. Hemp, which George Washington and Thomas Jefferson both recorded cultivating in their farm diaries, became a controlled substance by legislative proximity. While that ban held for 81 years, France issued commercial hempcrete building permits in the early 1990s. The UK built its first documented hempcrete structure in 1986. 3 decades of real-world performance data accumulated in Europe, while American builders had no legal access to the primary ingredient. The 2018 Farm Bill finally removed hemp from the Controlled Substances Act. But the Farm Bill only opened the agricultural door. The building code did not move with it. The International Residential Code, adopted in some form by 49 states, lists specific approved materials. A builder who deviates must navigate an alternative means and methods pathway requiring independent engineering review, third-party testing documentation, and a local variance approval. Hempcrete has no ASTM classification, no UL listing, and no prescriptive IRC pathway. In California, that alternative means process can cost between $15,000 and $40,000 in fees before a single wall is cast, according to cost disclosures from Americanvra, one of the state's first licensed hempcrete contractors. The seed is legal now, the permit still is not. 3 legal entry points exist right now for anyone who wants to build with hempcrete without the full IRC gauntlet. First, outbuildings. A workshop, garden studio, barn, or agricultural structure sits outside residential code in most rural counties and under owner-builder exemptions in many states. Build one. It gives you direct experience with mixing consistency, casting behavior, and curing timeline before any residential project is attempted. Second, geography. North Carolina, Colorado, and parts of the Pacific Northwest have the most developed permitting relationships, where specialists, including hempitecture and triangle hempcrete, have established alternative means packages that local building departments have previously approved. Using one of these builders on a first residential project can cut permitting time from years to months. Third, hemp wool. Hempitecture's prefabricated hempcrete bat product fits standard IRC stud bays, carries an R value of R3.7 per inch, requires no site mixing, and has a clearer permitting pathway because it integrates with existing prescriptive wall assemblies rather than replacing them. It costs roughly 2 to 3 times the price of equivalent fiberglass bats, but it is the fastest legal path to a hempcrete wall in a permitted residential structure available today. The material is available. The path to it just requires a map. One construction habit will ruin hempcrete faster than anything else, and it is the default move of every conventional contractor you will hire. Every mainstream insulation system is designed for a sealed wall. Fiberglass goes behind a poly-vapor barrier. Closed-cell spray foam is its own barrier. Modern construction logic says, keep moisture out by making the wall impermeable. Hempcrete requires the exact opposite. Its hygroscopic performance depends on the wall, moving vapor freely in both directions. Seal a hempcrete wall behind polyethylene, and you trap moisture with nowhere to go. You get the worst of both systems and the benefits of neither. The correct finish is lime plaster, breathable, vapor-open, antifungal, and documented across centuries of European masonry. Lime putty plaster on the interior. Hydraulic lime render on the exterior. Neither is what a drywall contractor will suggest by default, so specify it in writing before work begins. The curing window is the other constraint. A cast hempcrete wall needs 4 to 8 weeks of open-air carbonation before it reaches full stability. It cannot be enclosed or painted over during that period. Plan the construction sequence around it, it is not a problem, but it will not accommodate a standard build timeline without deliberate scheduling. Build hempcrete like a modern wall and you ruin it. Here is the spine of it. Hempcrete outperforms fiberglass on thermal buffering, moisture regulation, and carbon accounting by every independent measure available. It spent 81 years legally excluded from American construction, not because it failed any performance test, but because a 1,937 political net kept the plant out of American soil. The Farm Bill opened the agricultural door. 3 paths exist through the construction door right now: outbuildings, permitting-friendly states, and hemp wool bats. Your first move is the simplest one. Build something small, build it legal, and let the wall prove itself. If you want to see how a wall built from nothing but earth and straw outperforms a modern insulated cavity wall on every thermal metric, that video is next. Not professional advice, consult a qualified expert as needed.